And then from there, it was, all right, well, now that we know that, let's calcify it, right? Because we got to get to a point where we can do some calculus with this stuff. So areas, arc length in a polar plane. So what we're looking at is finding the area between curves, within a curve, and also the arc length, all right? So when you think about functions in a rectangular coordinate system, one of the things that you could do would be to find the length of the curve itself, but you could also find the area between the curve and the axis. This works a little bit differently because what's the axis? You know, we have the polar axis and that's about it, right? And our independent dependent variables are nowhere near what they were before. So we got a lot going on here, and we got to kind of parse this through and see what we can do. But what I wanted to do is reacquaint you with a formula that you may have seen in pre-calc. So I'm either reacquainting you with it or just acquainting you with it for the first time ever. And that is the area of a sector formula. All right. So area of a sector. So, well, first, I guess I should talk about what a sector is. It's a circular sector. If I draw a circle, and cut out a little wedge here. What I'd be looking at, or at least the part that I'm shading here, that would be the sector. All right. So it's a slice of pizza. That's all. You know, not Sicilian, of course, but not a delicious slice of Sicilian pizza from Calc Yonkers. So, but it's still a delightful slice. Now, we got a few things going on here, and I'll give you the short derivation of it, just because you know, I don't want to beat this to death too much, but this looks like a triangular region, right? So a sector of a circle is a triangular region. Therefore, we could think of the area as the same as the area of a triangle. So the area of the sector could also be thought of as half the base times the height. All right, so then the big question would be, all right, well, which part of that sector is the base and which part of it is the height? So that's where a nice diagram comes into play. So let me redraw. That's an ellipse. That's not what I wanted. There we go. But this time I'm going to do it without shading it in. All right, so we got that triangular region. I'm going to designate one part of it as being the base. That's this part. Eventually it'll show up on the big screen, but I'm just, that's the base. Now it's not a linear base, so that's going to make things a little weird, but the height I'm just going to bring it in, extreme close-up. Whoa. Oh, it's so small now. So I got a base and a height, right? The height is obviously not as easy to see, right? So the question would be, all right, well, what expression can I use to represent the base, and what expression can I use to represent the height? Well, the base, we'll start off with that. The base, ooh, I need this to be bigger. Is an arc length. And the geometric formula for arc length is S equals R theta. So that base, we're going to call R theta. All right, it's dependent on the value of theta. At this, you may remember this formula as the origin story behind the circumference formula, because if I put in a 2 pi for theta, I get 2 pi r, which is the circumference formula. Right, now the height, is a line segment that starts at the center of the circle and intersects with the circumference of the circle, also known as a radius. So that's a radius r. So the height can be replaced with an r. All right, so when I look at my area equals half the base times the height, I can really go after it with a substitution, replacing both the b and the h, respectively, b with an r theta, and h gets replaced with an r. And so we end up with the area of a sector formula of 1/2 r squared theta. All right, so that is the pre-calc formula. And really, I mean, I call it a pre-calc formula, but it's just a formula. You know, it's geometry formula. It's just a formula that's used to find a particular measure. All right, so 1/2 r squared theta. So that's great, but it only works if it's a circle. So it's not that great. But it leads us to something great, because if we look at any polar graph as being a collection of infinitely many circles, and that's going to require some explanation, I'll get to that in a second, then we could actually apply this relationship to any polar graph, right? So what's happening in this diagram here is you have r as some function of theta, right? So just thinking back to what we were looking at before, like r equals 1/2 sine theta, right? So something along those lines. But you can tell that based off this diagram that it's an arbitrary graph, you know, just some sort of r equation that's in terms of theta, but it's not as simple as a circle or an ellipse or something like that, where there's a known formula to determine its area, right? So what we do is we look at our start value and our end value, right? Theta equals alpha, theta equals beta, so start and end. In integral form, we tend to replace the alpha and betas with a's and b's just to make things a little easier, but it's supposed to be alphas and betas. Now, what we're going to do is we're going to start at that alpha and collect areas as we maneuver or move from alpha to beta, all right? So let me give you a quick example. I'm going to take one tiny little segment here. This little guy. I should have chosen a different color. This little guy here, all right? Now I'm going to try to draw a line segment. Oh, it actually worked. All right, this little sliver of fun here, that's going to be a circular sector. All right, now circular sector, but you just said that that formula only works for circles. This isn't a circle. How is that going to work? That's funny you should ask, right? So this is a sector of some circle. Some circle out there can be plotted so that just the tiniest little fragment of a sector would have this little depth to it, right? So what I can do is kind of, oh, that was shaping up to be terrible. Just imagine that this is part of a circle, some huge circle. Where this would be the center, this would be the radius, and we would have some value theta, but what we're going to do is we're going to look at this on an infinitesimal level, all right? Meaning, I don't want theta, I want a d theta. So this little movement here, this s, this arc length, I'll actually write arc length. Just this little guy here, going from the alpha value to the end of that little shaded area, that's the arc length, all right? But I want it to be so infinitesimally small that I don't create any gaps. If you think of Riemann sums from Calc 2, maybe Calc 1, what you were dealing with was having infinitesimal width rectangles. So the rectangles were very, very, very skinny to the point of having no width, right? The width approached 0. And so by making the width approach 0, you can collect infinitely many of those rectangles in the closed interval and fill in all the gaps, right? So another little segment here. Let's say I was going for this one. Let's give it a little bit more width. So this little sector, for example. Thank God for autocorrect. This is part of some huge circle. And it has its own arc length, all right? So we'll have infinitely many of those circles that we're compiling together. And when we put them all together, we get the exact area bounded within this region, right? But it's specifically related to the distance away from the origin. So we have to have an R and we have to have an arc length. Now that arc length, normally it would be S equals R theta, but now it's going to be S equals R, because the R would be defined based on the function R equals f of theta. So maybe it's not a particular value as in a constant, maybe it's like cosine of theta or something like that, but we'll know what R is. It's going to be R d theta, right? So if I want the area of an infinitesimal, I'm going to break out the Googler here. I say the word often enough, you'd think I know how to spell it. That would be 1/2 R squared d theta, all right? Because essentially I'm taking everything that I did over here. The only difference is instead of having a theta, I would be putting in a d theta, all right? But everything out, every other instance involving an R would stay put, all right? So that would give me one single infinitesimal sector. Now, if I want all of the sectors, the sum total of all of those areas, so take each infinitesimal sector and add it to every other infinitesimal sector, and eventually we'll get the bounded area. And so that's where this formula comes from, all right? So that's kind of like a more hand-wavy version or derivation or origin story behind a formula, but that's the general idea, right? Just to give you a little bit of background, because what people end up looking for is the quick hitter type technique like it was in Calc 2, where it's like, okay, so if I want to find the area under a curve, I just integrate it and that's about it, you know, from A to B. You know, and there were exceptions to that, but this is a lot different. You know, it has a lot of the same characteristics, the look and feel, but what people end up doing is they end up saying, okay, I'm just going to integrate the function and just call it a day, and that's nowhere near correct. All right. Area between polar graphs, that should make a little bit more sense based off of what we just did with the first equation or expression, because all that is finding the area twice and then subtracting. It's just you know, some clever manipulation of the formulas allow you to kind of make it a little bit more concise. But over the same interval, you'd have, so alpha, beta, you'd have 1/2 r squared d theta, but for the first function, and from that, we would be subtracting alpha beta 1/2 r squared d theta, but for the second function. And then you can see here that we have a common 1/2. That's where this 1/2 is coming from. And we have a common d theta. That's where this one is coming from. And so when you factor those out, let's chuck it over here. We get 1/2. We have the r squared and the r1 squared and the r2 squared. Those are going to be subtracted, and you have that d theta at the end. But those two guys are the only things that vary. Let me go red for those keeping score at home. It's going to be this guy minus this guy. And then we just slap the integration symbol around it with the appropriate bounds. So the moral of the story here is you don't really need a new formula as long as you know the original formula, that 1/2 r squared d theta, and you just apply a little bit of common sense, right? So that's really what I'm getting at there. Yeah, it's an adjustment, but it's a manageable adjustment. And when you see it in action, you realize it's not terrible. At least in the setup. The only thing that'll ever get you would be the difficulty level of any integrand. You know, if something is a little bit more complicated to integrate, you know, like involving like a trig substitution or something like that, then you could end up being in a little bit of hot water. But generally, it's never going to be too bad in terms of the setup. The arc length is I'm going to call that a different story for a different day. But what I wanted to do is just flip over to the next page and just take you through a simple case, and then leave you with a much more challenging case. You know, so I'm going to exercise my rights as a teacher to do the easy one in class, and then leave the god awful difficult one for you to do on your own. With the idea being that that we'll go over it next class anyway, so it's not like you're left to your own devices, right? But we're only going to focus on area right now, so we're not going to tackle the arc length just yet. Arc length's actually pretty easy in comparison, so we could do it, but I'm looking at the clock. So I have r equals 3 on the interval of 0 to 2 pi, right? So I'm just going to draw a quick sketch of that. Here's 0, here's 2 pi. It's a closed loop with a radius of 3. So we already know what the area is supposed to be because we can just use area equals pi r squared, but that's not the purpose of this, right? I put the theta step in there as a 0.01 because ordinarily I would use the graphing calculator, TI-84 graphing calculator, and that's the best theta step to get it to be curvy without taking too much time. But we're doing it by hand, so it doesn't really matter at this point. So you could ignore the theta step is really what I'm getting at. All right, so we know our rule. It's a single function. We're not finding the area in between two functions. So we're looking at alpha to beta, 1/2 r squared d theta. All right, so if there is no interruption between the pole and any point along the circumference of the circle or whatever the figure is, the polar graph, then you can just pop it right into the equation or into the expression and go from there. All right. But if there is some kind of interruption in that you have like a gap, you know, think washer method from Calc 2, you have some kind of gap, then you need to make adjustments, right? And that's a different example for a different day. So we'll cross that bridge next time. But this would be going from 0 to 2 pi. We'd have 1/2 r squared d theta, all right? Well, they tell us here that r is equal to 3, so 1/2 3 squared d theta. So on the interval of 0 to 2 pi, we're talking 9/2 d theta. All right, so now I just got to integrate. So it's a constant, so we're just slapping the variable on. 9/2 theta over the interval of 0 to 2 pi. Ordinary integration techniques apply, so fundamental theorem of calculus is in play here. So substitute your upper bound for quality 9. And substitute the lower bound, although that's not going to matter for much. And here we can see that we're looking at 9 pi as a result. So that's my area. All right. Now, pi r squared, area would be 9 pi because the radius is 3. 3 squared is 9. So we would have gotten the same value using an algebraic technique, or really not even algebraic, just computational. But this shows you a little bit more about where that formula came from to begin with. Next time, if I remember, actually, this is how I'll remember. I'll take it as a typo. So the first person, same idea on Remind, just send me include general example on page 14. I'll know what that means, and then I'll know to create the example and send it next time. But what I'll do is I'll have an example where I show you where the pi r squared formula came from using integral calculus. It's pretty cool, right? So I'm going to stop the recording. Yes.